We might do sense of these here.
Oh. You want to play like okay. You want to paper or sleep? The notes for others. They wanted to read it yesterday, but I didn't do the thing up. So I think the other thing is it's often helpful to start with the outer board because when you start this, then the lower board it gets covered in it. So it's just like all right, let's listen to Sahil.
Okay, before I start something, let me quickly correct something. I said something yesterday about foliation, which is not exactly correct. So, as Iri pointed out, so what I said was every two-dimensional foliation on S3 is looks like the foliation. But I also said that if this looks like the foliation means there is exactly one compact leaf which is homeomorphic to torus. So that's not true. There exists at least one. So there can be more than one. But what's known is that there exists at least one compact leaf which is diffeomorphic to torus and which bounds this reef component. That this torus which is bounding a solid torus. Inside the solid torus, the leaves are the ones that I constructed. There must exist one component. It's the correct statement. So, sorry about that. Yeah. Now, yesterday what we did was we defined foliation and we saw some examples, and then I related foliations with submersions. I showed that every submersions give a foliation, and locally every foliation is given by a submersion. So today I'll relate this foliation with other objects from differential geometry like vector fields and one forms. And so basically what we'll be looking at is the famous Frobenius theorem. I won't be proving it, but I'll state what it says, because I think that's the result where most of us actually see this term foliations when we use differential geometry. Okay, let me start with the definition of what a K distribution is. K distribution maybe denote it by delta. Then a distribution of M is actually a vector bundle. Rank K such that the fibers are subspecies of tangent space, such that for each point M, this fiber, thank you, this is k-dimensional subspace. So In other words, it's a tangent subbundle of rank K. Tangent subbundle. Okay. We have a tangent bundle of the manifold, and we are taking a k-dimensional subbundle. So this is what we call as a distribution, and so again, let me point out, this has nothing to do with the distribution that we use in differential equations and those things. This is a distribution in the sense of vector bundles, tangent. So let me come to the point how this comes in picture with foliations. Yeah. So before that, let me tell you how we get distribution. Let me relate this distribution with these objects that I was telling you, these vector fields and manifolds. So note if x1, x2, xk are a smooth vector field such that this x1, x1, xk they are linearly independent. So, by the way, a vector field is a section of tangent bundle. So at each point it gives us a vector. So that's what these are k vectors, and I'm saying that if these vectors are linearly independent for each point q, then we have a corresponding distribution to these vector fields, which is defined by at each point given by the span of this vector. This will give us a distribution. And in terms of let's say we need the same number of vector fields, linearly independent vector fields, to get a k distribution. The k vector fields to get a k distribution. So these are the vectors which are spanning this linear, this tangent subspace, the subspace, the k-dimensional subspace of the tangent space at each point. Now, in terms of one forms, so suppose if omega 1 up to omega k are one form, one forms again such that these are linearly independent. Then this subspace given by the intersection of the kernels of these one forms, which is let me denote it by this is the set of vectors in the tangent space at the point q, such that omega I be 0. This is 0 from 1 to k. This delta k, this delta is actually a n minus k distribution. So these are these are linear functionals on the set of vector fields or on the tangent spaces, not the vector fields, on the tangent spaces. So in terms of vectors, what we need is k number of linearly independent vectors to get a k-dimensional subspace, or we require n minus k number of linear functional to get a n minus k dimensional subspace. This which is just the kernel of each of these linear functions. So not just yeah, I'm taking the same number of objects. The k vector fits gives us a k distribution, but k number of one forms gives us a n minus k distribution. Okay. Let me start with every k-dimensional position has a corresponding.
Sorry?
Yeah.
So here we are calling that vector space is k distribution or a bundle of k distribution. Delta Q.
Yeah.
Span of this is k distribution.
So this is a fiber. This is the fiber. So this is a subspace of tangent space at the point Q. This is fiber, and collecting this fibers, we get this object delta. Yeah. Okay. So every k-dimensional formation defines k distribution, which we denote by denote by here. K distribution on M. So there is a k distribution corresponding to a k-dimensional formation. Let me tell you the fibers, what the fibers looks like in this case. Let be a point in the manifold. Now, by definition of
Distribution is a vector bundle or the section of that track.
the distribution is a vector bundle.
That's a vector.
Yeah.
So you get that for each field we have a vector space delta.
Yeah.
That means there's an assignment of each point be a k-dimensional.
That's exactly what a vector bundle is. At each point, you have this fiber, which is a vector space.
Vector one is a triple PEV. So P is a map from each for each.
Yeah.
Fibers are like
I was just
the vector part in the vector bundle is referred to the vector space, which is each fiber.
fibers are the sub.
Yeah. So
Fibers are the
sections.
vector bundle. Fibers are those vector spaces. So each delta Q is a vector space. Fiber is vector. It's like a tangent bundle. Each fiber is the tangent space at Q. So similarly, take a subspace. This delta Q will be a subspace in that.
So you take the trivial vector bundle. You have a manifold. You take M cross Rn. So the fibers are Rn. These are the fibers. These are the vector spaces. We do need to check some compatibility conditions, local triviality and all. But I think they will come from the fact that locally in the neighborhood they are given by this k vector fields. You can change these vector fields and to get local trivialization. Yeah, so by definition of a foliation is what are leaves? Leaves of foliation. Leaves are partitioning the manifold, and leaves by definition they comes out as equivalence classes of the equivalence relation, right? So there is a unique leaf passing through a point Q. And leaf of foliation passing through point Q. Now, locally, a leaf looks like a disk, open disk of k dimension, which is a plate. So if I take my point Q here, in local charts, the foliation is nothing but this parallel disk. So I have corresponding to Q, I have a unique k-dimensional tangent k-dimensional subspace of tangent space, which is the set of tangent vectors tangent to this k-dimensional disk. So at this point, I take this tangent space, which is spanned by this vector del by del x1 and del by del xk. So this is a local chart. This is a local chart where foliation looks like this parallel disk. Now this is the tangent subspace of dimension k. This we can pull back through the coordinate map. So here is my here is my manifold M. Here is my point Q. Now this is a foliation chart where P maps this domain into this. And pulling this back, we get this curve. We get the local picture of foliation in the manifold. Now this tangent subspace is this which we can pull back, fix chart of this and all over del x1, del by del xk, and this will be the fiber at the point Q. This is the entry. Is it fine or like there's some confusion with this assignment of vector subspace? Locally, these are parallel disk, and parallel disk, we know what the tangent subspace corresponding to this parallel disk. This is the vector subspace spanned by these vectors. Other vectors are in the transversal direction. Now we just pull back this subspace under P star. P is out diffeomorphism. We can do that. So it's still a k-dimensional subspace. We assign these subspace to each point Q, and in this case, the trivialization map actually comes from the foliation charts itself. Because if you take any point Q, you take a neighborhood. This so if I have this map pi from L, then this is here. So I'm denoting it by TF to the manifold. So the inverse image of the set U, if you think about it, in a foliation chart, this foliation looks like this. And in this case, each fiber is just the vector R2. This gives us the local trivializations. So this is actually a vector bundle, and since each fiber is a subspace of tangent bundle, tangent space, so it's a tangent subbundle. So it's actually these fibers constitutes they will give us a distribution, and this is the distribution corresponding to the foliation. This is by definition it's unique. There is distribution corresponding to foliation. This is unique. Okay, so what we have done, we have a foliation, and I assigned a distribution to this foliation. The main part is now the converse part. So if we just know what we just have a distribution, when can we say that it comes from a foliation? Now this question is answered by the famous Frobenius theorem. So let me state this. Okay, before I go to Frobenius theorem, let me a distribution delta is evolutive. This is invariant under the sleep bracket. If um, if for vector fields, even vector fields x and y belongs to delta P. If we take two vector fields which are contained in the distribution, so at each point the vector corresponding to this vector field is in the distribution itself. If we take two such vector fields, then the V bracket again a vector which will again belong to I'm hoping like this some part of the audience will be familiar with these notations or with these terminologies of V bracket and or. So it's not like you text returns with this V bracket, it can be think sort of as something like this, if this makes sense. So it's kind of what is a commutator of x and y. So if it is if the V bracket is again in the same subspace, same fiber of any two vector fields which are in this distribution, which correspond to this distribution, they say this distribution is involutive. In Frobenius theorem,
Force flow in the direction of X and flow in the
Oh,
direction
yeah,
of Y,
right.
that's the same as.
yeah, yeah. So I forgot about that description. Yeah. So there is a flow corresponding to each vector field. Now, what this condition says that not exactly this condition. I guess this being 0.
Yeah.
So x and y being 0, it means that if we go along the flow of x first, then y, or we go along the flow of y first and then x, it doesn't matter. It will still end up at the same. This this term will give us some kind of error. Like how far can these two objects be? There is another version of Frobenius curve. Let me first state this one, then I'll state the one in terms of one forms. It says let delta be a K distribution and delta is involutive and completely integrable exactly means this, that there is a corresponding foliation. There is a corresponding k-dimensional foliation of which this delta is a distribution, is a corresponding distribution. That is the foliation. Okay. Delta. It gives us condition when does a distribution gives us foliation. Now, I already converse part, and conversely, a distribution corresponding to a foliation, yes, is So we check that we assigned a k distribution to a foliation. This is also true that that distribution is also involutive. And if we start with the involutive distribution, then there is a foliation. So it gives us a if and only if condition. Now, note that one distribution is always let's say involutive, always involutive or integral. Always completely integral. We start with a one-dimensional tangent subbundle, then this involutive condition automatically holds. And these manifolds or the leaves in this case are actually given by the existence and uniqueness theorem for ODE. It's a high dimensional distribution in which we need to check these conditions. I won't go into the proof of this, but the idea would be basically so we start with the k vector fields locally. We start with k number of vector fields x1, x2, xk, which spans this distribution in a neighborhood. And what we know is that this will be a basis. So it's a k dimensional, and we are taking k number of independent. So we change coordinates, or we change this basis so that we change this basis so that we have this condition. These are vector fields, so that this may look like this. And given such vector fields which hold this condition, we can find another change of coordinates after the another change of coordinates, so that these vector fields actually becomes a coordinate vector fields. L by L. And these vector fields span the this parallel k disk, which is exactly what we have in this picture. So in the neighborhood, these vector fields are this constant del by del x or del by del xk, and the picture of this in the neighborhood, the position is given by this picture. So that's how we construct a position corresponding to a distribution. As I said, one distribution is always integrable. There is, given a one distribution, there is always a foliation corresponding to this. Let me give an example. We start with the let x be a non-vanishing smooth vector field on M. So, given a non-vanishing vector field on a manifold, it will generate a one distribution on M. The tangent subspace is just this one-dimensional subspace spanned by this one vector field, one direction. So, how do we assign this foliation corresponding to this? We have already seen from the idea that I gave. So, what we do is we consider this M. Here is my manifold M. Here is my Q. We consider this OD. Consider this differential equation dx by x. Say x beta of t, where beta is a map, let's say, from some neighborhood of 0 to M, and with initial condition that eta of 0 is the point Q. So what it says, like we are given a vector field. So at each point I have a unique vector. Right? Now starting with point Q, I'm solving this differential equation for which the solution always exists and is unique. So what I'm doing, I'm moving along these vectors. And I can do this at each point, although locally, but I can do this at each point. And extending these solutions, the global objects that we get are exactly the leaves of the foliation that we require. And the foliation chart in this case will be given by this result, called as straightening theorem. Vector fields. It says that if X is a vector field on M such that X at a point P is non-zero, it does not vanish at this point P, then there exists change of coordinates U, P around P such that in these coordinates the vector field looks like this constant vector field L by del X. So we can always straighten out a vector field if it is non-zero at some point in a neighborhood. And this exactly gives us, so if I'm taking, if this is my chart, given this, what are the level curves of this, not level curves, what are the integral curves of this vector field? These are these one-dimensional parallel disks. We solve this, solve the differential equation corresponding to this vector field. We get these curves, x1 equal to not x1 but x2, x and the other coordinates. These are given by x2, x n equal to constant. So the last n minus 1 variable constant. These are the integral curves of this differential equation, this vector field. We get a vector field. We get a foliation corresponding to each non-vanishing vector field. Now I can, let me take a specific take x to be let's say let me take a very easy one first. Take x to be this c times L by del x plus c1 plus c2 L by del y, where c1 and c2 are non-zero. We solve this vector. We solve this differential equation corresponding to this. Okay, even without solving, you can see this. What are the vectors? They are constant vectors, c1 and c2. So let's say this is the direction of c1, c2. This is our vector field. Of course, we can easily solve this vector differential equation because it's quite easy. Now we can see what the leaves in this case actually looks like. They are these lines. If we integrate along this direction, we get this. So the foliation is the foliation by lines. With the direction vector is given by the C1, C2. Let's take another vector field. This time, let's take a bit more difficult. So this is y n by del x minus x by del y. So this vector is actually orthogonal to the radial vector at each point, right? Take this vector field on R2 minus 0. Because at 0, this vector field is 0. We want the vector field to be non-vanishing. So our manifold is R2 minus 0. So at each point, so this is not here. At each point, the vector is like this. So if we take a circle here, what we can see is, because these vectors are orthogonal, again we can find out this leaves explicitly from solving this differential equation. But even from the picture, we can see what the leaves will look like. The leaves will be circles. Because at each point, the tangent line or the tangent vector on the circle is orthogonal to the radial direction. So the foliation here would be this concentric circle. Is this clear? This example, last example. Now let me state the other version of proving this theorem in terms of one forms. We move on to the next part. So proving this. So a K distribution
Is there a general definition that this leaves will be compact of the vector field? It's a compact.
Yeah.
Is there any condition on the vector field that it leaves compact?
Then this is just a special vector field in which this is. And it's not always that. Maybe we can change our vector field and then position might look like so. These are leaves. Again, this is not included. This is a leaf, and the leaves can be this hyperpolar.
The vector field is purely solution, then
If the vector field has
purely solution. In case the solution of purely, if you start with the point, it's back the point in the
yeah, so this comes
But constant is not given, but constant is period. But it is
and that's not that flow is starting at point A, A plus E times C1C.
It's a very strict condition.
Yeah.
You can have all sorts of. I mean, that's
they can be bounded, but even boundedness won't suffice as this compactness. They might approach this point, this weird point, which is we have already removed, might approach this point in a weird way.
it's not even close.
This,
Not even
this,
close.
they might not.
Like in this picture, it's not.
These
They are not close.
these are not closed, but these are
Yeah, these are not close.
these are not closed because of they are closed in R2 minus 0, but they are not closed in R2. So these are the kind of motivation, these are kind of picture of singular foliations, which are not yet going into. I'll come to this for this singular foliation when I discuss holomorphic foliation, but these are like the pictures of singular foliation. These are the singular points. So let me give you this combination version corresponding to this one force. So let's say a K distribution given by, let me write it in this term, given by or defined by this one form omega 1 omega n minus k. So note that I'm taking K distribution, so I need n minus k number of one forms. One form, and this delta, this is integrable or completely integrable if and only if this d omega I wedge omega 1 wedge omega n minus k. This is 0 for all I from 1 to n. this is Frobenius condition on the one forms to get to have this on K distributions. That the distribution comes from a foliation. As a special case, if K is n minus 1, so we have this not rank 1. This distribution is n minus 1 dimensional. That is, at each point I'm taking the n minus 1 dimensional subspace of the tangent space. In that case, I just need one holomorphic, one form, right? One form. Then so this delta will correspond to a one form omega, and this delta is completely integrable, or there is a foliation if this omega wedge t omega. If I only have one form, then this is the only condition from this. Now let me give you an example. So what the foliation here would be? It would be an n minus 1 dimensional foliation. So that's what we call codimensional foliation. Here would be 1 dimensional, 4 dimensional. Same. 4 dimension as in the dimension of the transverse. Okay, so let me give you an example. So consider this one form omega on, say, summation x xi equal to n. Consider this one form on Rn minus 0. Because at 0, this vector, this one form does vanish. We want non-vanishing one form, so that they do give us one-dimensional space, one-dimensional subspace of the tangent. Now, I can write omega. First of all, let's check the condition. The condition is true because this omega is closed. If you calculate omega, this is d omega is 0. The same coordinate d xi. So d omega is 0 means omega wedge d omega. Our condition is satisfied for the Frobenius curve. So there is a one-dimensional n minus 1 dimensional solution corresponding to this. Now we can find this explicitly because not only omega is closed, but omega is exact. We can write omega to be d of 1 square. Right? So what will happen is the leaves that we get of the position will now become the level curves of this map. Now this will be a subversion on Rn minus 0, and the level curves gives us the foliation. So the foliation, let me just make this picture in R2. So this is not included. So again, the foliation is by sphere and spheres. Is it fine?
Second one,
Yeah.
from that condition, we find that we can
You mean going from one forms to? Yeah.
one.
Okay, so you mean the relation between these two?
From that condition,
Mhm.
so that we get such vector fields.
Yeah, I mean, from what I guess, this vector fields, we can complete this basis of tangent subspace to a basis of tangent space. So we'll have this complementary vector fields xk plus 1 and xn, and we have a corresponding basis of this tangent cotangent bundle, and those complementary bases maybe I don't know if they will work exactly like that, or we need to change those. I guess they should.
Renewal of the
Yeah. So this is how we can work.
But then to go from that formula to this involutive condition, you probably have to use that lead, the kata. And
Yes, yeah, right. So it's not like a very
what is that?
yes.
Like you take the derivative of omega with respect to like it's from almost certainly will follow from that.
Okay, so this is all about like this Frobenius theorem. So now we have related our foliation with these three important objects. Now there are many other objects which are linked with foliation, some group actions or something, which like foliations do comes from group actions and it's the algebras as well. Lead groups maybe something. So there are many ways of constructing foliation, but I just mentioned a few, and we can see that these are important ones because I've already showed you that foliation locally is given by submersion. Now again, as I'm saying, a 4-dimension one foliation, a one form satisfying this condition, giving us a n-1 dimensional foliation. So for n-1 dimensional foliation, even the converse is true. If we have a n-1 dimensional foliation, locally it is given by one form which satisfies the integrality condition. And same for vector fields. A one-dimensional foliation locally is given by vector field, non-vanishing vector locally. So these converse parts are locally. I'll go into these results when I go into this holomorphic foliation, because there I will be focusing on dimension 1 and 4-dimension 1 foliation. So here I'm not presenting this converse part because it's the same. We are not using anything about the holomorphicity in those results. Those proofs will work here also, the converse part. But before going into this holomorphic case, let me go.
Such a case, exact. Omega is exact.
No,
The boundaries.
You mean in the local
Omega,
case?
omega, with d omega equals 0.
I mean, if this is non-singular, then yeah, because what we are working, we have a foliation. Locally, the leaves look like this parallel n-1 disk. So the one forms corresponding to this would be dz1, dzn. Dzn is exact, at least in the nib. It's this exactness problem comes when there are singularities. Sorry. So he said, I said that even the converse part is true, that given a n-1 dimensional foliation, locally we can find one forms which defines the position in the table. So he said, are those forms exact as well? So if yeah, for non-singular position, yes, they are very nice one forms, dzn. But when there are singularities and we are looking at the position near singular points, then no, not necessary.
Maybe since you talked about group foliation comes from group action, I think you already mentioned when you talked about torus example, because you said like it was the part to cushion set, and that is a group action, and we did say that.
But the foliation is not coming from group action.
You said right that foliations for R2 is that are inheriting that foliations inherits foliation in torus.
Right.
You mentioned something like that.
So the group action was of Z2 on R2,
Yes.
which was giving us torus.
Yes. So what group action on the manifold?
Yeah. So group action on manifold, for which the trajectories or the orbits gives us foliation.
Okay, that's not an example of what.
No, that's an example of getting like we are getting torus from R2 by the group action of Z2.
You want to be able to recover the leaf using the compaction.
Yeah.
Something that gives you the foliage, which for these dense orbits would be
Yeah, I mean, in that case, the
for the situation where you have these dense orbits.
it was just lines of irrational
Yeah,
spots.
so would there be an action that recovers that?
Yeah, the RH, there will be RH. That's not on the place.
No, on the hard.
He's right that you
Yeah, on torus, yes.
or you can just
It's
just
just
yes or
action
no.
by R.
Another example is for the
Mm-hmm.
push it out by the lower one, and the other one is slack on the lower. I don't know what it does, but
Yeah. So, yeah, let me suppose to at 11, right? Okay.
Let us start.
No, I have just started the second part. Okay, so now let's start focusing on leaves of this foliation that I have defined. I said that these leaves are not nice all the time. Then
Sorry, I have one question.
yes.
This question asked in many ways, but it's related. So you basically said that instead of foliation, you have a relation, right? Like this is one of the
Yeah.
But I guess nobody is a converse also, I suppose. But,
Well, actually, a vector bundle is a foliation.
right. Oh, I see.
I mean, that's by submersion theorem only. I mean, it was the map from vector bundle
You
to.
also get global, you also get global.
Yeah, I mean, the global leaves would be the fibers. So, a vector bundle, by definition, there is a map from vector bundle to the manifold, which is a submersion.
I see.
So, by submersion example, the vector bundle will have a foliation exactly of the dimension of a vector bundle minus the dimension of manifold. So, and the leaf will be fibers.
Oh, you're doing it.
Yeah, the rank of the vector bundle.
You're looking at the global space, the global space, the vector bundle and mapping it.
Yeah.
Bundle actually subspace of a tangent bundle, right? Subbundle.
No,
In
not
general,
necessarily.
can we do it in
No, not necessarily. Like vector bundle is a manifold in itself. So we are claiming a position on vector bundle. So we don't need the tangent. We don't need the vector bundle to have anything to do with the tangent bundle.
We can sphere and take a bundle on a mini RN. Then there will be a function.
Maybe, so you're saying this is reduce a, yeah, this is reduce a foliation on the
Vector bundle.
Total space. So
Yeah.
vector bundle is always the
So
total
that's right,
space.
but we
Yeah.
they're looking for foliation from the pattern, right?
Yeah.
No.
What is the question?
No.
Sorry. First of all, everybody is thinking of the
Yeah,
vector
okay.
bundle as you should think of it as just lots of vector spaces on each point. That's
Yeah.
the whole point of a vector
Yeah.
bundle.
So when I'm
No,
saying
but this point is, one of the earlier was that if you had a foliation in the period, right? So I want to know if the converse, like of it, locally, there was a relation of vector bundle. When you give a foliation, right? I guess not the vector
Yes.
bundle. You want to.
You already have a distribution.
Yeah.
okay. Foliations. So as I mentioned, the leaves are not always nice, but they are equivalence classes of some equivalence relation. So we have this map I from the manifold to the manifold. Now this, by this position, I mean it's quotiented by the equivalence relation. This is a quotient map. Remember, I said P and Q are equivalent. I gave it in a definition of plaques, but now we know what leaves are. 2 points are equivalent if and only P and Q are in same leaf. That's exactly how we define leaf. So now this is the quotient map corresponding to this, and this is the space of leaves. This is the space of equivalence classes. Now this will give us a topology on the space of leaves, but in general this topology is not nice. It might not even be Hausdorff, as we see from examples of reef and those examples of torus where these leaves are dense. We cannot always separate these leaves. So this topology here is not always very nice. But again, we are going to see now. But this behavior of leaves is not always very chaotic. Like it's not like on this part it's quite dense and all, and on other part it's very nice. We'll see that it will stay uniform on all parts of the manifold. When I say uniform, what I mean in local charts, it will have the same behavior in the foliation charts or local charts. Okay, let's start with the definition. Let A subset of manifold M the saturation of A denoted by FA. So this is by definition is set of all points y in M such that y is equivalent to x for some x in A. We have some subset of the manifold. This is basically nothing but we are taking all equivalence classes of points of A. So what are equivalence classes? Equivalence classes are the leaves. So we take any point on A, we take the whole leaf passing through this point, and we take the union of all such leaves. And this is what our saturation of our set is in a manifold. In other words, we can write FA as I inverse of union of Lx x in A. So this is the description of our saturations of our set.
Quick question. In terms of vector field, it's everything that you can flow through from it.
From where? Sorry.
Like if I associate a vector field with
Yeah.
distribution to the foliation, then these are all effectively all the points that you can reach by flowing.
Yeah. In terms of vector fields, it's this flow. Yeah, the points where you can go along the flow of the vector field.
All the points that you can reach by.
Yeah. Let me start with the proposition. Okay, thank you. For the dimension, we need important with my result here. I get P dimension position on M. The saturation FA open for open set A. If we start with the open set, the saturation of this open set will be open. My proof will be more tutorial. I'll make some pictures and try to tell you how this works. Okay, so first of all, this clearly is our original set is a subset of our saturation. This is true. Now, let Q be a point in M such that but so since A is open, we already know there is a neighborhood around Q. What we want to show that we take any other point outside A in this saturation and we show that there is a neighborhood of Q which is in FA, and that shows that this saturation set FA is open. Now, how to see this? So let me show this. First of all, what we can do, we have this point P. Let me start with some point P in A, and then I have the saturation of this at A. And here, let's say I have a point Q. Now, the point P, so I take the leaf passing through NQ. So it will intersect A, because the saturation of FA is the union of all leaves of points A. So it will intersect A. Now we take any point in this intersection and call it as point P. Okay. Now, by definition, when we define this, we said that 2 points are equivalent if there is a sequence of flakes connecting these 2 points. That is, I have these flakes. Flakes like this. Flakes come from local charts. And again, I can refine my coordinate charts so that I get this condition. Need this condition. One intersection U2 is non-empty, and this U1 union U2 contained in a position chart. So if I start with an atlas, I can refine this atlas and get smaller coordinate charts which satisfy this condition that if 2 of these charts intersect, then the union of this set will be contained in one coordinate chart, one big coordinate chart, one big foliation chart. Now, with this property, I claim that it is. I'm kind of claiming that it's enough, it's sufficient to consider that the path of flakes is just of length 2. We just need two flakes. Is it visible? Okay, so we only need to take 2 flakes, and then we can repeat the argument to get to the point Q and get a neighborhood around Q.
So here we are choosing such chart, right, which satisfy this property, but it's not for every.
Yeah, so we can start with an atlas. We have this because a foliation I assigned a maximal atlas. I can start with an atlas of this maximal atlas. I can refine this and get these charts.
This is satisfied, right? For every it will not be true. For every chart.
No, I'm refining and taking those coordinate charts which satisfy this condition.
Okay.
And I can do this. I can find these coordinate charts which cover manifold and satisfy this property. So now, if I'm taking 2 flakes, what happens is I have this. First of all, I have this big coordinate chart, and I have these two coordinate charts. This is u2, this is u1, and here is my point P, here is point Q. Now, here is these are the leaves or the flakes corresponding to chart U1. And corresponding to U2, these are the flakes. Union. I mean, intersection is understanding something defining so that I have the global chart where these are horizontal, nice. Then I can use this. Okay, so this picture, what I have. So here is my point Q, and here is my point P. Now I know there is a P belongs to A. P belongs to A, so there is some neighborhood of A, which P, which is in A. Now let's take this vertical thing. So at each point, if I take this leaf in this chart, this will be in F2. A plate is a part of a leaf. Now at each point here in this neighborhood is in A. So the leaf corresponding to these points are in FA. So in this local chart, at least what I have is I have, let's say, this kind of set which is in FA. This is in FA.
I don't understand how by refining we can make sure that condition holds. Like how exactly do we refine? What sets do we take and what do we not take? And what subsets do we
So
take?
it's a atlas. So you start with U.
Yeah.
You start with U. You take a point, take a very small neighborhood, and say take the same coordinate chart.
So that U1, U2 can be any two foliation charts, right?
Yeah, any two foliation charts which now satisfy, which are refined. These are
In
refined.
that atlas, if any two foliation charts intersect, there is a bigger foliation chart.
Yeah.
You might have to take like more of the if you take that many plates, I think you might have to take more steps.
Yeah.
You might have to take those smaller as well. So if there's not time for any I think you can make them small.
This latest number, right? Even cover, you can take smaller cover in the intersection map to going to this. Included inside a bigger cover, right?
Okay.
So I want to understand two strategy. So I got what you do. I guess first your so the idea is basically go back where you hit some point,
Yeah.
right? Take a neighborhood and then flow it forward.
Exactly. That's the
Right?
idea.
But right now you may have multiple dimensions. You may not. You're trying to find the vector field, right?
Yeah, the vector field, because these vector fields or this, so
Yeah,
there's
yeah,
more
yeah.
than one vector field. But the vector fields are nice in this local chart. These are del by del x1, del by del x. These spans this formation of the leaves. So I get this neighborhood and I transfer it to another chart. Now this chart on the intersection, because I said this is my set in which is in F8. Now if we look at this is in U1. Now if we look at U2, what we get is we get some sort of set like this, which was coming from U1. This part, this intersect with this set. Now this is in FA, and the plates are again still this parallel disk. Since this is in FA and the intersection, okay, so this plate passing through this point, we call it alpha 1, and this call it alpha 2. So this is the plate that I mentioned that we need two-step plate. Now alpha 1 intersection alpha 2 is known as they are intersecting. So let's say this is the point Q, this is alpha 2. So alpha 2 does intersect this open set. And if we take the saturation of this open set, it will be this. At least this set is in U2, which is in FA. Again, now this is in the set of FA. We get the neighborhood of Q. We get a neighborhood of Q from here, which is in FA. And if this Q is far enough, we can do it in some finitely many steps. This is how we prove. This tells us that this is open. Last, if you have a question.
So then you have to iterate to the whole thing, right? This is for two
charts. Yes. Now we have got some neighborhood here.
So we are using this projection map is open, right? So we are using this map.
Which this map? No. I think this is proving this map is open.
Yeah.
So this is like proving this map to be open.
Why? So you had some point the region of the intersection you extended along the foliation. Why is that set open? So like you had a subset in U2.
Yeah. So this set. This set.
Yeah, and then you just consider all the foliations coming from
Yeah.
that.
So take any point here in this neighborhood. The whole leaf will be in the saturation. So then what is the leaf? Or at least the plate. This is the plate.
Yeah. So why? My question is why the resulting set is open when you take the union of all
In
the
local charts, so this point is what? It's x1 now y. So y is constant along these plates. So I'm taking, so the saturation of this point will be in this open set. It will be a set of points x, comma y. Y is constant. Let's say y naught. X, comma y, such that x belongs to the some open set W1, which is n disk. So saturation of a point is k dimensional disk, which is exactly the plane, and y is varying in an open set in transversal. So this will give us. You can take it from submersion thing. We can project our open set the way I give submersions. I can project it on this transversal, this vertical object, and what are the level curves? Or this submersion, when we take the inverse image of this whole set or the open set, it will still remain open. Now this is the open set. This one is this.
Should we have done something like induction as well? Like here we showed it for PQ where they are both in the like next to each
So
other.
that's what you have to do. If
Yeah.
the point Q is
If
far enough,
distant away.
yeah, this is the picture.
Yeah.
So we shift our neighborhood to a point here, and
Right.
at some finite element point, we get a neighborhood of
So, can you use similar technique to show if A is closed, then F of A is closed or something like that? Or not really?
Actually, no,
Or
that's
maybe
not.
not, yeah,
but
single point, yeah.
yeah, but that's not.
Okay.
Leaves are not closed.
Leaves are not closed, so.
Also, there isn't a, I mean, I think this is going back to a previous question of saying, even though there's a distribution, there isn't a global flow necessarily.
Yeah. Local is.
That is my question.
Yeah, because your distribution may not have a choice of, it may not have a trivializing frame of bases.
One way is true.
Like if you take sphere, let's say orbits are spheres, then the distribution will be tangent spaces of the spheres, and in certain directions you will not be able to choose a frame. To get a flow, you need a frame of the
Right.
distribution.
So the only thing is the thing we to is how much I can avoid choose. It will not be great, but I think it will. Right. So like right here.
No, yes.
Yeah.
Locally, yeah. That means, yeah. So So can I think of a flow going from Q back to B, taking a neighborhood and then flowing it out? Because is that
Along the flat, along small pieces, yes, but globally you don't have it.
Yeah, I mean, you could always flow a couple of times.
Yeah.
on different flows.
So that's basically what you do, right?
Yeah.
It takes small things and then keep
Yeah.
flowing and then you have to
Yeah.
treat.
Like over there, you have a nice flow.
Right,
So you
right,
can flow a little bit, flow a little bit.
So you have to keep relabeling.
Yeah, it's like trying to trivialize your vector quantities. You can do it till a certain point of time, but there's gonna be some monotone, you're going to have some problems with the.
There is global flow which is restricted to this flow. and
Then it's
then
fine.
we can-
Yeah, then.
I mean, the foliation is given by one vector field, let's say. Then we have one flow.
So that puts a very strong restriction on the topology of these peaks. I mean, you have a flow like.
I guess the point of leaves is to go beyond that, right? Because you gather a lot more.
We can start with some complete applications or something like
Right,
this.
to begin with, yeah.
One more result about line before finishing. Before that, we say that A is invariant. Okay, so I'm assuming there's a position in the definition. I'm assuming there's a position. Then I'm calling a subset A of a manifold and is invariant. So invariant under T, under the foliation, invariant or saturated. In the foliation. If the saturation of the foliation, saturation of the set is set. If it's already saturated. As a small exercise. So suppose that we have an invariant set. Invariant. Then do that the interior and the boundary. They are both invariant. Yeah. So if we have an invariant set, the interior of this invariant set, the closure of the boundary, they are all invariant.
They might not have any interior. It can be.
The saturation of empty set is empty, right? So
Some set is dense, then also it doesn't.
if some set is dense, yeah.
Sorry.
Yeah, if it is dense on this, if what is that set in deep space, then it will be dense on the whole space, right? Saturation of that.
If we start with a
Will be
dense set,
dense subset of the deep space, that will be dense subset of the that will be my definition.
maybe we need to check something.
Is then saturated.
Yeah, then the saturation is already
The deep
dense.
space is there, there will be some dense subset, then the saturation.
You only need to take subset of leaves and then look at it saturated.
Let me give you another definition. Sigma be a submanifold. Say that, so I'm using this term transversal, although I have not defined it. Let me define this term properly. We say that sigma is transversal to the foliation. Transversal to the foliation. And only this. So if this satisfies this condition, since sigma is a submanifold, there is a tangent subspace or tangent space corresponding to this with this tangent subspace along with the tangent subspace of the foliation. This spans the whole tangent space of the manifold. This is true for all these. Sigma plus V1 plus. And we say sigma is a transverse section. Transverse section. Not only this condition satisfies, but dimension of sigma, dimension of TIFR, is the dimension of M, which is, or you can say the dimension of actual manifold, no, not tangent one. It says that they are kind of it's a direct sum. We are writing this instead of this is a direct sum. Yeah. So there are no tangent vectors, no tangent vectors in the intersection. Yeah. The transversal, means transversal is correct. I think the main part is transverse section. Section is exactly say kind of vertical direction.
Sahil, can we see example in the case of torus with this standard foliation of transversal and what is this?
So I mean transversal as she said, we can take whole.
Or just the opposite. I mean, right section would be the opposite.
Opposite.
So we can take let's say this is a foliation. Let's even a curve like this.
The single curve is fine.
Yeah, it's transversal.
But that will not satisfy that condition at each point P, right?
Yeah.
You want
No. Each point P of the manifold, no, the submanifold. Sigma.
okay. Then
Only on sigma.
I thought for each point in.
Only on the submanifold.
Really that if your foliated space was the total space, you really are taking a section of your vector.
I don't use transfer section was a bad name.
So you're taking a section of your foliation of total space. Here it's like a section of that circle bundle.
Exactly.
Torus example, what will be a saturation?
So individual orbits are like saturation.
I mean, if you take a point A, thus set A to be a singleton point, the saturation is just a leaf. But if you take, let's say, some interval or some curve, if I'm taking the position to be the dense one, not in this case. If I take this position and I take, let's say, this transversal, this small part, then it's just this part. This part. Cylinder, right? But if I take the whole transversal like this, then the saturation of this transversal is the whole piece. Let me state a fact and then I'll give a result. So from an example of reed foliation or this torus example when we have the dense leaves, we observe that leaf and come back to coordinate position chart. Finitely many times. So in the torus case, we take any position chart because the leaves are dense. They of course they will come infinitely often to the same position chart. In the case of reed foliation, we need to take a coordinate chart on the compact leaf. because all other leaves are kind of accumulating on this compact leaf. So we take a foliation chart near a point on this compact leaf. We will have this condition that leaves are coming to this. So here is my foliation chart locally. So what can happen is I take a leaf L and I take the intersection with the coordinate chart U. This could be union of plaques alpha I. This could be some infinite union. And although we can say something, we can say that this is countable. We can at least name countable in the sense that we can start with a countable atlas. We can start with a countable cover of the manifold by foliation chart, and by definition, a leaf is like a path of plaques, right? 2 points in a leaf. So there can be only countable number of such paths which are possible, so that we can come back to the same foliation chart. So these alpha i's, they can be countable. They can be at most countable. And somehow this behavior of a leaf in a foliation chart, this remains uniform all over the manifold. If this is countable in the foliation chart, then okay, so yeah, not a countable thing, but the discreteness of these set, these plaques. Discreteness in the sense the number of. I'll rewrite this in terms of transversals. So here is my transversal. So the intersection of these leaves with this transversal, sigma. So here is my transversal. Whether this is discrete or this is countable, what this will remain uniform all over the manifold. Let me just state the theorem and then I can finish regarding this. F with 2 points, P1 and P2 in L, there exists transverse section sigma 1 and sigma 2 and respectively, and a diffeomorphism from sigma 1 to sigma 2 such that for any leaf L, L prime, F of L prime intersection sigma 1 this is true for all leaves.
Yeah, saying that this transverse section locally always exists.
Yeah, this is by looking at local this foliation chart, because foliation chart, this leaves are nice parallel disc. You can just take the complementary disc in the dimension n minus k. That will be a transverse section. Transverse section you can just pull back to the coordinate chart. That's actually the transverse section. Time right now to prove this, but this is what it says. So geometrically, if we take 2 points P1 and P2 in the same leaf, in the same leaf L, then then there exists transversal sigma 1 and sigma 2, and there is a map from this transversal to the transversal at V2, such that if you take any other leaf and the behavior of this leaf or the intersection of this leaf near this transversal will be same in some, okay, it will not intersect here, but it will have the same behavior on any other coordinate. Okay, this constructing this transversal sigma 1 and sigma 2 is not difficult because we just by local charts we can do it. It's the part of constructing this diffeomorphism from one section to another. This, if you have, I might do it in next lecture, but this is coming from the same idea as we define monotomy or holonomy map. What we do is we take, we follow the same procedure. We take those foliation chart, we take a path of plates, which kind of takes from P to Q, and we take points in the intersection. So we kind of partition this path from P to Q. We take a partition such that this partition point, these points intermediate, they are in the intersection of alternate open sets. Now, what we do is we take sections at each of these points in the intersection, and for adjacent sections, this map F is just a projection because they are in this U cross V chart. And composing these maps gives us the diffeomorphism F.
Can you just keep the code down?
I guess let's thank you.
I need to fix the problem. So you have 3 minutes less than what you can do.
Yeah, well, you cannot say what is
The room issues are all fixed. None of the course.
something. But it's always dependent on cost.
So very good.
Means
Okay. So the curtains are fixed. Okay. And the interior is
today I did ask him, he said they are
so my I forgot and it takes something like 5 or 10 minutes because the whole line has to get closed. Okay, I'll check.
means I'll ask him again today.
Yeah, I'll also talk.
Yes.
And I had one example for the question you had asked to like give a solution of a manifold. Then you like take R3 and then divide it into 2 half planes, z less than equal to 0 and z greater than 0. In z less than equal to 0 have like lines parallel to y axis, and in z greater than 0 have lines parallel to x axis.
Okay, but then intersection.
No, there it's y axis. Till there it's y axis, then after that is x axis.
Somebody, as I said, don't try to do it in art, but there are physical ways to do it in art. Just take one line like this and all other like this.
But this is
Instead of, but don't take these points. We don't take them.
okay.
It's a partition.
Yeah. But if I don't take these points, then which points am I taking on this line?
Which line? No, no. This line is complete. We are not taking these points for it. So this is one part. This one.
Okay, okay. It's separated into two lines.
Yeah. And then the example that I had in mind was more like based on foliations or singular foliations.
Okay.
So you want on R2 you have this foliation, right? R2 minus 0.
Yes.
It's the all lines passing through.
Yes. Yes.
It's on R2 minus 0.
Yes.
Now you take this on R3. You have this direction. Take the same one.
So like radial or what? Just
No,
radial.
no, so you have this plane.
Yeah.
Now this is the R2 third axis. Yes. Take the same information.
Okay. Okay. Okay.
Now this point, now we can add this because this point will become a line.
Yeah, we can add that one. Yes.
Right? Now all these are one line.
Yes. Yes.
Now this gives us a partition of R3,
Based on.
but it's not a partition.
Yes.
Now we have talking only on that. Limit
constant. It also would.
That's what I thought you said. It was very difficult to explain.
हाँ संजॉय भी तो था। संजॉय भराली क्या कुछ लाइक भराली ने गुलाम को बोला था कि तुम लोग का है वो किस रिगार्ड में था आउट ऑफ दी ट्रांसलेट वाला ही था।
हाँ हाँ almost the equation if the splitting function is constant or something that domain is homogeneous or the converse is trivial the domain is homogeneous and splitting function must be constant because the parabola is invariant but does the converse holds so it probably not then probably was looking for it because if I were prepared that the word is the guy Golam excited about Golam বসে ওটা তো বলে তারপর গোলাম হাজার পেপার they have considered squeezing function with respect to some domains which are something symmetry like balance so वो जो आंसरটা কি ছিল what the answer already gave that if you consider a domain and consider the squeezing function with respect to balance convex domain which is non-homogeneous balance convex or non-homogeneous then the squeezing function is identically equal to 1 with respect to that non-homogeneous but by construction the domain is not homogeneous constant does not imply that that domain should be homogeneous but the amount of the question was something different we have
No, if you take any complex maybe the question was speaking was with respect to what?
oh that's what that's
The model domain was
but we have some discussion about that question
You missed that.
we have discussed আমি বলেছি মানে তুমি একটা সিঙ্গল কোয়ান্টাম ডোমেন মানে সেটা একটা কন্ট্রাডিকশন আসতে হবে অনুরোধ একটা সেটা নিয়ে মানে বাট সাম ক্লাস অফ ডোমেন
But still he asked for you the only thing you can answer from where he said that is the advancement मिला है इस क्वेश्चन पे उसमें
अगर तुम मॉडल में चेंज करते हो तो टेक एनी कॉम्प्लेक्स डोमेन which is not homogeneous then splitting function of that domain with respect to that domain is one.
Oh, but it is not. But he was taking model as.
But actually, I think it does not.
True.
Does not answer for
This question is different.
The B is from
more general question can be asked. That is, if a domain has constant splitting function, but the splitting function is measured with respect to some homogeneous. Does it
It's a wall.
That's a more general.
Why is it required?
No.
That
मॉडल डोमेन आप चेंज नहीं कर सकते आप बोल रहे हैं होमोजेनियस नहीं चाहिए तभी तो बना होगा ना ए सुनिए
Okay. Oh no, I took it out. I won't have it correctly. And so I'll stop this at the get some more of these defined numbers so they can simplify. I think I started the second you cannot control. The only way to control that is by taking out the value. So that matter. I think because I just always laugh while it's completely bad. I'm happily bad. I'll come back into this. I'll just use it as